In this model, we will study light propagating principle, that is total internal reflection. As we know that speed of light depends on the medium through which it propagates. So lighter is the medium, higher is the speed of the light, and denser is the medium, lower is the speed of the light. Speed of light in vacuum is 3 into 10 raised to 8 meter per second, and speed of the light in water is 2.26 into 10 raised to 8 meter per second. Speed of light in acrylic is 1.76 into 10 raised to 8 meter per second. Here acrylic is having higher density, that is it is denser medium than the water, and water is the denser medium as compared to the vacuum. That is why the speed of the light in vacuum is higher than the speed of light in water, and the speed of the light in water is higher than the speed of the light in acrylic. Index of refraction. So it is very important term related to the optical fiber. Index of refraction is nothing but it is the ratio of speed of the light in vacuum to the speed of the light in the medium. N is equal to C upon V, where N is the index of refraction, C is the velocity of the light in the vacuum, and V is the velocity of the light in the medium through which light propagates. The picture shows very good example of total internal reflection. In this picture, the tortoise is swimming inside the water, and the water surface acts as a mirror. So the mirror image will be formed on the surface of the water. Here the inside surface of the water acts as a mirror. Total internal reflection. This diagram shows the incident ray, refracted ray, angle of incidence, angle of refraction, and normal. Here two mediums are shown, glass and the air. The refractive index of the glass is N1 and the refractive index of air is N2. So N1 is greater than N2. So here when the light ray incident and the boundary surface, it will be refracted in the air medium. So here it forms the angle of incidence theta I and angle of refraction theta r. So this diagram shows the light source and the rays are incident on the surface between two mediums. So here as the angle of incidence increases, the angle of refraction also increases. You can see when the angle of incidence is 20 degree, the angle of refraction is 27 degree. When angle of incidence is increased to 30 degree, the angle of refraction is 42 degree. As we increase the angle of incidence again, so for 40 degree, the angle of refraction is 59 degree. A stage will come at which the angle of refraction becomes 90 degree. The angle of incidence at which the angle of refraction becomes 90 degree is called critical angle. So if we try to increase the incidence angle greater than critical angle, then what will happen? The ray will totally internally reflected back. That is, the angle of refraction will become greater than 90 degree. At the critical angle, the ray will propagate along the boundary surface, we can say. As the angle of incidence increases, the angle of refraction increases. Here the diagram shows the critical angle and total internal reflection. Here the critical angle is 48.8 degrees Celsius, at which angle of refraction is 90 degree. If we try to increase the critical angle greater than 48.8 degree, then what will happen? All the energy will be reflected back within the same medium. Here angle of incidence is 60 degree, and we can see that all the rays will be reflected within the same medium. This is the total internal reflection. We can summarize the total internal reflection. If the incidence angle is increased beyond the critical angle, the light is no longer refracted. Instead, it is reflected back inside the medium. This is called total internal reflection. When incident angle is greater than critical angle, there is no refracted rays. All the emergent rays are internally reflected.